the kinetic measurements, and we are going to discuss about the 4 different techniques for the kinetic measurement, especially the diffusion coefficient, measurement of a diffusion coefficient of the electroactive species in the cathode material is our main concern, okay? Kinetic measurements. Technique. Now we start out with the assumptions first, and then assumptions. First, charge transfer reaction. At electrode electrolyte interface is rapid. So charge transfer reaction means electroactive species, and this is electrolyte. And an electron is going to be supplied to have neutral atoms for the these reactions. We think this happens during the discharge. So it's not a rate limiting step in any sense. Okay, that's what we are going to assume. And the ionic transport in electrolyte is not rate limiting. Rapid enough, okay? This means that voltage that we measure across the electrolyte between the cathode and anode is a direct measure of the activity A at So let's say if we have cathode. An electrolyte. Okay. Then at some point we're going to have a concentration profile like this, okay, and discharging reactions. Discharging or if we do the charging, then we're going to have a concentration profile of electroactive species like this. Okay, this is charging. And the Nernst equation, the concentration which determines the voltage between the cathode and anode is the concentration here, not anywhere else. Okay, so we call this at x equal to 0. The concentration of electroactive species at the x equals 0 is important, not anything else. Now, what we are going to do is we're going to solve Fick's second law, where concentration gradient is now going to be round x that is the Fick's second law, right? And with the proper boundary conditions for each technique, we want to solve this problem. And you can notice that the solution is not a simple one. It's going to be very complicated, but we can have some physical sense at the very beginning or very final end at around the equilibrium. The equation, the solution becomes simple so that we can have some physical meaning in understanding the solutions of the solutions. So the techniques that I'm going to introduce here is 4 techniques, and let's see. Last time, as far as the kinetics is concerned, we have talked about the diffusion coefficient, chemical diffusion coefficient, and the relationship between the intrinsic self-diffusion coefficient by thermodynamic enhancement law, right? Thermodynamic enhancement factor that we have discussed the last time. And another important is the Einstein relations, which is the self-diffusion coefficient and the mobilities, the relationship between these two by the mobility kT and diffusion coefficients ZIQ, that should be equal. Okay, that is the Einstein relations. Nernst Einstein relations. These 2 things we have discussed the last time, okay? And now we are going to talk about talk about the kinetic measurement, especially the diffusion coefficient measurement, and with electrochemical technique. All right, so let's start with say we have a potential static method, galvanostatic method, and galvanostatic method, and we're going to talk about potentiometric method. And finally, the most powerful technique, which is going to be called AC impedance spectrum. AC impedance spectrum. And we are going to talk about up to here in this lecture. And then next week, on Monday, I'm going to a couple of lectures devoted for this AC impedance spectrum analysis. Okay? Now, in potentiostatic method, what you do is you apply the voltage, that is the EMF, the voltage, and the time, and you suddenly apply at the time is equal to 0, and you fix the voltage. And then, accordingly, you are going to measure the current between the cathode and anode, okay? And then you see the current is going to decrease in this fashion, all right? By the way, when you measure and apply the input, the voltage or current, the system that you're going to use is usually, this is we call the working electrode, and that is cathode. Okay, and then we have counter electrode, that is anode, and this anode is a sink or source of electroactive species, right? And we usually have another electrode here, we call the reference electrode, to measure the voltage or current on the cathode with respect to the reference electrode. And the reason why we use a separate reference electrode for this measurement is to eliminate the polarization effect and things like that. That is for elimination of polarization effect, etc. Okay, so that's what we usually do. We have a 3-electrode system. So if you have a lithium battery system, for example, you have a cathode for the LMO, LCO, LFE, whatever, and then for the counter electrode and reference electrode, you can use a lithium. Okay. Okay, in this case, now we want to solve the fixed second law, and now we have to see the boundary conditions which is going to be set. So initially, C naught of species A, electroactive species in A, and the concentration and E naught is the equilibrium potential. Before we are doing anything, okay? And the new CS, the surface concentration, will be maintained by application of delta E, okay? A certain voltage, equilibrium voltage, E naught, and then we increase or decrease the new values by delta E. Then according to this delta E, new surface concentration will be set depending on the Nernst equation, okay, at the surface. At x equal to 0. This is the important fact. At x equal to 0. And then time dependent current by Fick's first law. All right. The IT now is equal to, should be related to the flux that has been flown by concentration gradient at x equal to 0, and then the current is going to be related with this parameters here, and S is the cross-sectional area. Cross-sectional area. So in this case, conditions for second Fick's law solution. Now it's going to be C equal to C naught at X is equal to L. L is the length of the cathode. Initially, this is the initial conditions. And C equal to CS at X equal to 0 for the time after the application. we could fix the surface concentration like this, and then the flux according to the fixed first law is going to be 0 at x equal to L for time greater than 0. This means at the far end, infinite long length is going to be assumed. Then the solution, we are not going to derive the solution for this, but solutions for time greater than the, this is a characteristic length, okay? L square over D is called the characteristic length. For this, the solution is going to be not over CS, C naught, and then there is a series, 0 to infinity. L minus x over 2 dt square root it's going to look like this. And for time greater than L square over D, then we're going to have another solution for this, which is xt minus c s over c naught minus 4 pi. In sine well, and IT now is equal to ZFS CS minus C naught and the current. Now we're talking about this profile, okay? To the FSD CS minus C naught over L exponential minus pi square over D T over 4L square if T is greater than L square over D. And after equilibrium, CS or C naught is equal to I dt F volume. Now, since there is a constant concentration, okay, volume simple. And since volume is nothing but length and thickness and the surface area, we can see that the current change is going to be QL D over pi T the short time. And IT Okay, this is what we can measure the current with respect to the time. Okay, and then this is the curve can be analyzed in the short time and the long time like this. Okay, so this means that the IT versus 1 over root T from IT versus 1 over root T, the slope is related to the diffusion coefficient of the material from this equation, right? So at the very beginning, if you take the I versus square root of T, 1 over square root of T, then you're going to get the diffusion coefficient from the slope. And in the long time, log I versus T from the I versus T plot we can get the diffusion coefficient. The slope is related to the diffusion coefficient and the long time with this equation, right? So this is how we can determine the diffusion coefficient of electroactive species inside the cathode material. And you can do the same thing for the galvanostatic method. And in galvanostatic method, we are going to use the different boundary conditions. Okay. In a galvanostatic method, you have a current here, and then for a certain period of time, let's make it a little longer. Okay, t equal to 0 to t1, and you set some current, you pass the current between the two electrodes, and you monitor the voltage change with respect to the time. Now, before you put any current, it has some voltages like a V naught equilibrium voltages, and suddenly you apply the voltage, apply the current, you're going to have IR drop. This is a voltage related to the IR drop, okay? And then the current, the voltage is going to change because of the current that you apply. And at the time you have cut off the current, then this IR is going to be restored, the same amount here, it's an IR drop. And then it's going to decay to the some point which is different now from this V naught to some values here. And then the difference here is going to be delta E now. And that's come from the fact that you have been inserted or removed the electroactive species by passing the current I naught in this galvanostatic method, okay? So constant in the galvanostatic method, constant flux of a species A is maintained. At electrolyte interface. Is equal to 0. So with this experiments, now the initial conditions and boundary conditions for fixed second law is that the C equal to C naught throughout the cathode thickness as the initial condition. And now you're going to apply constant current, which is related to the diffusion coefficient, the flux according to the fixed first law, at x equal to 0 for the time you begin to apply the current. Now again, at the end, you do not have any flux. Okay? And you put these boundary conditions you're going to have a solution for the galvanostatic method. CXT C naught is equal to, it becomes pretty complicated. And the definition of complementary function here, complementary function is exponential minus s squared. Well, for short time, then the equation becomes and Cs, the surface concentration is going to be changed because we constantly we apply some current, some flux of electroactive species at the surface. So now this time, in this technique, we are not going to fix the surface concentration. The surface concentration is going to be changed because we apply some fixed current during the experiment, okay? And so I AVM over ZFS pi D and then DE D delta. So with this, we can set the diffusion coefficient now is equal to 4 over pi IB VM over ZFS square. This is not a subscript A, this is A on the top, and this is not a subscript B, this is B on the top, something like that. Okay, and then dE over d delta divided by dE dt 1/2 skip. Here the C is equal to A plus delta over B VM, where VM molar volume of A B equal to 3 over N, where N is number of So you can see this is the slope of kilometer titration curve, right? That is the slope of the Coulomb local slope of the kilometer titration curve. And for small current, of course, d over d delta is linear. dE over d root t also linear. Okay. And if you measure d, the potential with respect to root square root of t, then you can see extrapolate this, and that this much is going to be IR drop. So we can, here the R, it includes the resistance of electrode lead contact, electrolyte, electrical resistance, yeah, it includes these two things. So maybe this electrolyte resistance is related with the spacing between electrodes. Okay, it's going to be related with the electrolyte resistance, and that is the contact resistance. And of course, this IR drop, IR is not a function of time. It's not going to be changed with respect to the time, right? It's a fixed value. At the long time, the first two terms of the infinite series C st minus c0 it over So you can see the voltage change in the galvanostatic technique. You can measure the diffusion coefficient from the coulometric titration curve slope here. Okay, this is the slope at the coulometric titration curve. Next week on Monday, I will continue the potentiometric method. But I just want to show you that this is my PhD, Stanford University PhD work, my work on the thesis. You can see this is the y-axis is the diffusion coefficient of lithium in the potassium hexatungstate, okay? And potassium hexatungstate is electrochromic materials. I tried to make a thin film of potassium tungstate, and then I want to use that as a color change with lithium insertion and removal. And I want to know the diffusion coefficient of lithium inside the potassium hexatungstate, and this is the concentration of lithium. Now, in normal practice, in a fixed second law, we just assume that diffusion coefficient is not changing with the concentration of lithium in the hexatungstate. But it turned out that as you move from here to here, this is a Y in LIY, and the potassium hexatungstate here, and then the diffusion coefficient is changing from 10 to minus 8 to 10 to minus 9, 10 to minus 6 and 10 to minus 9 here. That's the room temperature, and you can see a lot of data points, diffusion coefficient with respect to the lithium concentration in the lithium potassium hexatungstate, thin film. Well, this is one of the examples how powerful the electrochemical technique is to determine the diffusion coefficient. If you use the conventional or classical methodologies to determine the diffusion coefficient at one fixed value of your sample, it'll take many hours just to determine just one point of a diffusion coefficient at some specific concentration of lithium. Okay, and so in order to finish this kind of data may take you a year or so. And if you are doing the conventional or classical methodological processes to determine the diffusion coefficient. But with the electrochemical technique, you have to set the coulometric titration curve to find the slope here. And then these values, molar volumes and B stoichiometric values, if you use a thin film, then that is a very small amount, so that it can be equilibrated very quickly, so that you can have data points very quickly and very precise, as you can see here. Okay. Okay. So. We are going to talk about the potentiometric and the AC impedance spectrums next week on Monday. Okay?